Welcome everyone to today's HPC Café. My name is Georg Hager. Today's topic is power and energy consumption of HPC systems, because we think that this is something that comes up in discussions a lot, also when talking to the general public about HPC. They always ask how much power does that need and where does power go? And oh my God, it goes up the chimney. So it's really important to know the basics of this. This is not a scientific talk. I could give a scientific talk about power consumption, but that would require much more time and much more preparation. So I'll stick to the basics. So first of all, we're taking a specific point of view here. If you take the point of view of an end user of computing devices like mobile devices, your cell phone, okay, your tablet, then of course the stuff that's important to you is different from an HPC user. Here's a marketing picture from Qualcomm from more than 10 years ago. And it shows quite clearly what's important as an end user. You want a long battery life of your cell phone. Okay? You are ready to make compromises regarding performance. It doesn't matter, for me at least, whether the browser opens in 0.2 or 0.3 seconds. I don't care. But I do care if my phone lasts 2 days or 4 days. Okay, so I'm very happy with a long-lasting phone, even if the performance is not that brilliant. But that's just me. But I think this is valid for most. And for most users of mobile devices. Okay, so this is the specific point of view of a mobile device user. That's not the point of view we take in high-performance computing. So what's the point of view in high-performance computing? So first of all, the scientists, I call them nerd, okay? They want to run some simulations, so they get a CPU time or GPU time allocation. I've chosen here Margaret Hamilton as the prototype nerd. Do you know who that is? She led the team which developed the software for the Apollo flight computer, which brought people to the moon. Very significant achievement. She's also a software engineer, self-taught. I'm putting her here because she's like a prototype nerd. She's not the type of nerd that has put out a lot of papers, but I found that picture to be really nice with that stack of code, actually the code of the Apollo flight computer firmware. And what you want to do as a scientist is you want to use your CPU time allocation to produce science, okay, new insight. So that means in our world, you want to write papers. So to boost your recognition, to push the boundaries of science, to put it a little bit more philosophically. Okay, so that's your goal. You get the CPU time, you run your jobs, you get some insight, you run models, whatever, and then you publish it. That's a very simplistic view of the whole story. As computing center people, and I call us naggers, as computing center people, that's not the only goal we have when running those systems. So first of all, we're concerned with the cost of the system. We have to buy the system, we have to set up infrastructure like cooling, power supply, and so on. All that costs money. It costs maintenance, it costs support in terms of staff, for example. It costs energy. Okay, the more power the system uses, the more we pay for that power. Of course, there's also some science. We're happy if you do science on it, because that gives us a way next time to procure a bigger system, because you need that for your science. And then there's the next machine. The whole cycle begins again. But the question is, what is our metric for success in this whole game? As a scientist, you want to do science. You want to publish your science. Okay? So number of papers per CPU hour would be a fitting metric. I want to be blunt. But as a computing center, the metric is not quite clear. Especially if the cost for infrastructure and especially energy sort of outweighs the cost for the pure hardware. And we'll see about that in a minute. So let's talk about power consumption of HPC systems. And the fact that this is significant is for everybody to see if you go to top500.org, which is a site which lists the 500 fastest supercomputers in the world. It's updated twice a year, once in November at a conference in the USA, and once in June at a conference in Germany. So this is the latest top 5 of the top 500 list, and it lists the performance of a specific benchmark called LinPack that those systems achieved. And this is the metric by which this list is ordered. So this is here Rmax, and you see the first 2 systems are beyond, just slightly, but beyond 1 exaflop. So they crossed the exaflop barrier 1 year ago. And you also see that there's significant power consumption coming with that. So the top 1 system consumes about 23 megawatts of power, and the number 2, 38 or 39 megawatts of power. So that's a significant amount of power consumption for these systems. And then The first European system is Lumi in Finland. We still get something like 7 megawatts of power. So modern computing centers, if you want to play in the first league, you have to calculate with several tens of megawatts of power if you really want to get into the top 10. And that's expensive. But that's the first thing. And the second thing is there might be environmental concerns, because if you burn a lot of electrical power, there might be lots of CO2 emissions, and you don't want that. Okay. Now, about the CO2 emissions, I looked at the FAU website, and it shows us that for the electricity supply of the whole university, FAU purchases 100% certified green electricity, renewable. Okay, so that's good for your conscience. Fine, don't worry about CO2 anymore. And that's what I'm going to do in this talk. Okay, for me, the main concern is cost. What does it cost to burn that much energy? And is it relevant, and can we do something about it? If you want to know more about the FAU strategy for energy saving, there's this link, and you'll get the slides afterwards, of course. All right, so what does it mean to run a computer? And to put it bluntly, a computer is a device that turns electrical power into heat. That's what it does, okay? You plug it into the wall plug, it consumes 1 kilowatt, 2 kilowatt, 3 kilowatts, and what comes out is heat. That's it. And of course, you have to get rid of that heat. That's one thing. And it's very simple to calculate if you have the power consumption, so the power dissipation in watts, which I call W, and the runtime of your computer, the time over which the system is operating, this is T, then the product of the two is the energy that you burn in joules or kilowatt hours or whatever. And of course, you have to get rid of that heat, as I said. Of course, to do that in different means. You could use water cooling and cool down the water with a chiller, or as we do it with Fritz, for example, you could use chillers on the roof of your facility to cool down the water with ambient air, which comes at really low cost. Okay, all you have to do is pump the water up to the roof, let nature do its thing, and then get it back and cool again. Okay, so the cooling itself, the infrastructure, may come at some limited cost, but still you have to supply the electrical power, and in the end, you put it all into the air. Of course, in reality, this power dissipation W is not constant, because different programs are running on the computer, and maybe sometimes not fully utilized, like on weekends or on the holidays. So this power consumption, power dissipation W depends on T, typically. Now, I will, for the most part of this talk, I will ignore this property, that the power consumption may vary. Of course, if you do scientific analysis of power consumption, you have to take this into account. Okay, even in one program, there could be phases where the power consumption of your computer is low and then it's high again, depending on what exactly your CPUs are doing. So if you want to save power for whatever reason, saving CO2 or saving money, there are two tuning knobs you can turn. One is the time. How much time do I need to run my code, my program, or how much time is the computer actually turned on? And the power dissipation. So we can either reduce the time or reduce the power dissipation to reduce the overall energy, and that's what we pay for. Okay, if you look at your electricity bill, it's kilowatt hours you pay for. Now, 1 kilowatt hour is a certain amount of money, and I'll come to that. Now, the amount of energy that we burn with a typical HPC system here at NHR FAU, if we take the Fritz cluster, under full load, it consumes something like close to 700 kilowatts. 650, sometimes a little bit beyond 700. For 1 year, that's 5.7 million kilowatt hours. Okay, that's a number. To put that into perspective, that's about 1,500 standard German households. Okay, 24/7. Okay, that's the amount of energy we burn. That may seem a lot, 1,500 households, but if you think of other experimental setups and high-profile experiments like a wind tunnel, for example. A wind tunnel for CFD experiments also consumes several megawatts of power. So that's not, in the grand scheme of things, it's not something that's a huge amount of energy. However, the problem we have here is that the power we need for the HPC system is some very high-quality power, electrical energy, and it has to be delivered at a very tiny point in space in our computing center, maybe a space that's as small as 10 by 10 meters. Okay, and then once you've done that and you run your computer, you have to get rid of the heat, and that's another challenge. All right, so So much for the actual power consumption and the energy. So keep in mind about 1,500 standard households. Now, what about the price? What about the money that costs? We assume here, and that's really a moving target, but I'm assuming about 30 euro cents per kilowatt hour. Okay, that's something you have to pay. Now, 1 euro Fritz, that's 650 kilowatts times 8,700 hours times 30 cents. That's 1.7 million euros on the energy bill. Now, if we assume that Fritz will have an operating time of like 6 years, to keep the math simple, that's 10 million euros just for the energy bill, assuming that the price of energy stays constant. That is more than the system actually cost. Okay, and that is actually something that stayed the same over the last at least 15 years. The amount of money you spend for operating the cluster in terms of energy is more or at least comparable to the hardware cost. That's a typical insight in this whole business. All right, so this is for the whole of Fritz. Of course, this is a little bit of a pessimistic assumption. I'm assuming here that every node burns with its full power, 650 watts or something. Okay, so that's maybe an assumption that's too pessimistic. Usually, on average, one Fritz node is at like 400 watts, 500 watts, something like that. And I'll come to how that decomposes into different parts of the cluster. So how much does my job cost per day? Of course, you're a user. You don't use all of Fritz all day, all of Alex all day. You only use a couple of CPUs or a couple of GPUs for at most 24 hours. So how much does that cost? One node of Fritz at full power is about 4.70 euro. One GPU of Alex, which is about 300 watts, a little bit more, that's an average value, plus some share of the host, because there are host CPUs, there's a host motherboard, there's networking infrastructure, and so on. I'm assuming 20 watts for that. For 24 hours, that's about 2.30 euro. Okay, so that's a fair amount, but keep in mind, we have over 600 GPUs in Alex and over 1,000 nodes in Fritz, because it accumulates. And that does not include the cooling infrastructure. Now, fortunately on Fritz, we have hot water cooling, as I told you. So we use water to cool the CPUs and the RAM in Fritz. We pump it to the roof and we cool it down with ambient air. That comes at almost no cost, maybe 5 to 10% overhead. For Alex, it's more because it's air cooled, but still under control. Still, this power, we put it in, we take it out of the plug, the wall plug, we put it into our systems, we do something with it. Of course, we produce science, but then in the end, it goes out the chimney. Okay? And that's one major concern of the general public. We had the Lange Nacht der Wissenschaften in October last year, and people came in and asked about our systems, of course, and we told them, yeah, there's Fritz, it's a fast computer and takes 700 kilowatts of power. And they asked, oh my God, where's all that heat going? And we had to say, okay, it's going out the chimney. Of course, you can do something about that. You can use it to heat buildings. You can put it into the district heating systems, things like that. And this is going to happen for the next generation of buildings we build here, but not currently. Currently, it's actually going up the chimney. Well, not quite, okay, because you get something from it. By pumping that much energy through your system, you get science because you run simulations. Of course, we have to be aware that burning so much power, every kilowatt has to be well spent. Okay, and I said something about that later. All right, so I told you on Fritz, we have about 650 watts per node. On Alex, we have something like 3 to 4 kilowatts per node. How does that decompose into the components of the systems? Because if you want to do something about the energy consumption, you need to know where all this energy is burned. So I've made these pretty diagrams. I was told these are called Sankey graphs, and there's a free tool you can use to do them. On the left, we see the composition of the power consumption of a Fritz node. I'm assuming 700 watts of power. Of that, the CPUs and the RAM running at full power, okay, thermal design power, so the highest possible power output, consume about 540 watts. So 3/4 of the overall power is the CPU and the RAM. And if you look at the decomposition into CPUs and RAM, you see the RAM is really a minor part of that. This wasn't always the case. If you remember EMI, on EMI, the RAM consumed a lot of power, but not on Fritz for some reason. So in essence, you can say the major part of the power is actually the CPUs. So if you want to save power, if you want to save energy, you want to make the CPUs burn less energy. The rest of the system is almost negligible. We have some network infrastructure with maybe 20 watts The power supply has some loss, which is between 5 and 10%, depending on how well utilized the power supply is. So I put it here with something like 56 watts, and there's the rest of the system. There's a motherboard, there's other stuff. Okay, but the majority is really the CPUs. On an Alex node, it's surprisingly similar, at least concerning the division between the computing devices and the rest of the system. On an Alex node, Alex A100 node, we have 8 GPUs, and each one has a thermal design limit of 375 watts. For the A40s, that's about 100 watts less than that. So overall, those 8 GPUs can burn 3 kilowatts if everything is fully utilized. And then we have 2 CPUs plus RAM. The thermal design power of one CPU in Alex is 225 watts, so I put here with 220. So again, about 3/4 of the system of the power is spent in the GPUs. Typically, on a typical GPU heavy job, that's where the power is dissipated, and the CPUs are quite often quite idle. One contribution that's not to be neglected if you really want to do exact analysis is the fans. So we can actually read off the fans from the infrastructure sensors, and the fans can burn as much as 300 watts just for pumping the air through the system. All right, so again, these are upper limits, and the rest is eyeballed to give you a rough estimate of what's going on. Again, the take-home message is the computing devices burn most of the power. The rest of the system is just a constant baseline that you have to take into account, because the shorter your job runs, the less time you need, so the less energy you burn also in this constant baseline. So it is significant, but not dominant. All right, let's look closer into the chips themselves. So in the chips, we have CPU cores that actually execute your programs, that do multiplications and additions. That's the work that you're interested in. Okay, that's the work that you want them to do, multiplies and adds. But there's other work that has to be done. For example, data has to be fetched from memory into the CPU and stored back in order to make that happen. Okay, there has to be some data to crunch if you want to crunch. So data transfers are another important part. So how much of the energy burned in a CPU goes into data transfers, and how much goes into actual computation? And the answer is quite surprising. The actual computation today on modern CPUs takes far less than 50% of the power. Okay, so also the chip area. The most of the chip area is today taken up by caches and other infrastructure. The actual computational units, where the music plays, so to speak, that's a minor part of the chip. And it burns a significant part, but not a dominant part of the overall energy. Most of the energy is spent in data transfers. So all else being equal, even the performance being equal, if you can reduce the amount of data that you move through the system, you will do something good for the energy consumption of your code. Because data transfer is the #1 energy consumer in a computer system. And of course, also the further away data is, the longer the wire, the longer the latency to get the data, the more energy it costs. And there have been studies more than 10 years ago, and also some interesting predictions which may or may not have come true. If you transfer one element, 8 bytes, one element of data over some InfiniBand wire, that's an insane amount of energy compared to transferring the same amount of data from the cache to the registers of the CPU. That is true. However, the good news is long-distance data lines like networks, they cost a lot of energy per byte, but they also transfer very little data per second. Okay. Within the CPU, you have on Fritz 36 cores. Every one of those cores has a level 1 cache, a level 2 cache, a share of the L3 cache, and a share of the rest infrastructure, memory interface, and so on. And all these things work in parallel. So even if you look at one data path and how much energy it costs to transfer some data from A to B, that might be a minor amount, but it accumulates over the whole chip. And overall, even though per byte InfiniBand is very expensive, overall it's a minor contribution to the power consumption of the system. Most of the power is still spent in the CPUs. One more thing, and I come back to that later, the power consumption is significant even if the chip is idle. And I don't mean actually idle, not running anything. By idle, I mean an extrapolated idle power that you get when you extrapolate to 0 resources utilized, so no cores. I'll have some data about that later. Now you know the ballpark of those numbers and where the energy is spent. 75% is in the computing devices. Most of that is data transfer. Now, how do I know how much energy and power my job uses? And there's a lot of tools that can give that information to you. I'm concentrating here on what's available here at NHR and FAU. Now, for CPUs, there are lots of tools. Basically, reading power information from CPUs has been facilitated a lot by Intel about 15 years ago by introducing the RAPL interface. RAPL stands for Running Average Power Limit. It's actually a means of capping the power consumption of the CPU, but it can also be used for measuring the power and the energy of the CPU. You can use these counters from your programs and make it easier. There are tools to help you with that. One tool is contained in the Liquid tool suite, which you may know. It's developed here at NHR and FAU, and it's also available as a module on our clusters. Now, if you want to know, for example, how much energy your single node multi-threaded program spends on a Fritz node, you can use Liquid perf counter like this. You say, I want to measure energy. There are many other metrics you can measure, like data transfers, flops, whatever. And you need to specify where you want to measure, so all 72 cores, and then you wrap your program with it. Then it gives you an account of how much power you burned, average power in watts, and how much energy you burned in joules. That's quite nice. So you can play around with clock frequencies and other knobs I will tell you about later and see how much that influences the power. If you have a multi-node job, you have to use MPI run to start it. There's also a wrapper, Liquid MPI run, and you can use with it also the same functionality. You can also measure hardware performance counters, including energy. Now that's very invasive. Of course, you have to change your scripting, your setup, how you start the program, and so on. A much easier way is Cluster Cockpit. You may know it. There was an HPC Café like a year ago also about Cluster Cockpit. It's based on Liquid in the backend, so it uses the Liquid functions to measure the energy of all the jobs running on our clusters. It's a free tool. You can download it and install it if you like, if you're hard-nosed. And I'll show you a screenshot on the next slide. So Cluster Cockpit is a job-specific monitoring software that lets you look at your jobs and see what your jobs do to the hardware, how much performance they have, how much memory bandwidth they use, and how much energy, how much power they burn. On the GPU, it's a little bit thinner. There are NVIDIA tools and AMD tools, NVIDIA SMI and ROCm SMI, which show you a point measurement of the current power dissipation. So it tells you right now you're burning 300 watts on this A100 GPU. That is possible. Also, Cluster Cockpit has, for the GPU jobs, it uses NVIDIA SMI in the background to measure the power consumption of your GPUs. Now, power consumption measurement is a difficult task. Imagine a job that has phases that alternates between a very hot phase, doing lots of computations, data transfers, and a very cold phase, maybe communicating or waiting for memory a lot. Okay, so it may alternate between high power and low power phases. And then the question is, if you do a point measurement of the power, how much information does that give you, and is it accurate? Because if these phases alternate on a millisecond basis, then you may see only a fraction of the true picture. So these power measurements always have to be taken with a grain of salt. So Cluster Cockpit, you can access it from the HPC portal. If you go to your user tab, there will be a green button, go to Cluster Cockpit, or I don't know if it's called that, but you will see it. And if you do that, you will see all your jobs running and also your finished jobs. We keep a track record of every job so that you can look at metrics like CPU load, CPU frequency, CPU performance, GPU utilization, and also GPU power. So here in this diagram, it's highly configurable, so it doesn't have to be at this place in your display. You see that in this case, these GPUs, it was an 8 GPU job, ran at 125 watts, which is low for an A100, okay, which has a TDP of 375. So it's running at a low power level for whatever reason, I don't know. I just picked this job because it was nice to look at. So this data is available, and you can look at your own data, of course. We as admins can look at all your data, and if there's anything noteworthy, anything weird, we will send you a ticket. Okay, so use that. And if you need more information on that, I can send you, or look up our HPC Café track record. There's a video about how to use Cluster Cockpit. All right, Now, what about reducing the energy? Let's say you want to reduce the energy. You want to help us spend less money. Of course, you might not care, okay? Because we're not charging for kilowatt hours. We're charging CPU hours or GPU hours. So you don't care, actually. But if you want to do something good, okay? So how do you do that? Now, first of all, and I told you how that is the #1 optimization strategy, you could reduce the job's runtime. If you reduce the runtime of your job and everything else stays constant, usually you burn less energy. This is the #1 rule, like the zeroth order rule of energy consumption of computer systems. It also has a lot of good side effects. You use the resources better, okay? If you have a certain number of jobs you want to run, and you reduce every job duration by 25%, you use 25% less resources. That means somebody else could use those resources, which are now free. Good, you're a good person. Or you could do more science with your CPU time allotment. Also good for you. So more science per CPU hour. The power dissipation, so the wattage, may change also. If you optimize your code, sometimes the power goes up because you're making better use of the hardware. Computing faster means it could burn more power. It can also go down because you may choose a totally different algorithm that uses less resources. And just a better algorithm that has a cooler footprint on the CPU or GPU, so power may also go down. So it could go either way. This is the starting situation. You're running like 3 jobs until your the CPU time allocation runs out. This is the red dashed line. And then you optimize something in the same allotment. You now get 4 jobs. So that's good. That's for your science. But you might see that the cost of that by burning a little bit more power. So it costs more money in the long run. Of course, we run the system for 6 years, no matter how hot or cold your jobs are. Okay, so if you optimize your code to make it run faster and burn more power, we pay more in terms of energy. Now, the second tuning knob you can use is the actual power dissipation. So you don't touch the code of the job, but you do something to the hardware or to the way you run the code in order to make the wattage lower, to have lower power dissipation. Now, that may mean you lose some performance. And the #1 knob to do that is clock frequency. If you reduce the clock frequency of your device, your CPU, for example, chances are your job will run longer. Okay, but as you will see, there's a lot of potential to save energy in that, at least for certain kinds of jobs. So it may be cooler, okay, but it takes longer. You get less science per CPU hour. That's bad for you, but good for us because we run the system for 6 years, okay? And if you burn less power, we pay less for the energy. Okay, so what could we do to do that? What are the tuning knobs? And sorry for this complicated slide now. I'm just trying to put everything into one slide to show you what are the knobs and what they can do for you. So if you optimize the code, there are 3 things you can observe: power dissipation, so watt, energy, watt hours, and CPU and GPU hour utilization, how well you can utilize your allotment. You get 1 million CPU hours. How well is that utilized? You optimize it. So if you optimize the code, power could go up or down. I mentioned that. Okay, and that, of course, has an impact on the energy consumption. The energy will typically go down, even if the power goes up. That's a general rule. There's a tiny little part of the configuration space where you make your code faster, it runs faster, it finishes earlier, and in the end, you still burn more energy. But that's an exception. Usually, making the code faster burns less energy. And of course, you're making better use of your allotment. Okay, so that's good. Use less CPU and GPU hours. The second tuning knob is clock speed reduction, so underclocking. By default, on Fritz, for example, the CPUs are running in turbo mode, so the CPU has some freedom to choose a clock speed even above the base clock speed that's put on its case. But you can play with that. Okay? You can set a clock frequency that is lower than that. So what happens to power? It will inevitably go down. If you reduce the clock speed, power will go down. That's for sure. The energy may go up or down. I will show data later. So if you reduce the clock speed too much, your program will run much longer. If the program runs very long, then the whole baseline power, all the stuff that is in the system that has constant power dissipation, like the fans. They're not constant, but they have a certain baseline. The motherboard components and so on and so on. All this will dominate the energy consumption. So if you make it too slow, energy goes up. It may go either way. For your CPU time allotment, well, hopefully it doesn't change a lot. I have examples later where we show that both things can happen. And third, and something that you may not have on the radar, is what I call concurrency problem. Use less hardware to do the job. Use less hardware per job to run your program. And that can have different flavors. You could use fewer nodes for your multi-node job, or you could use fewer cores on the chip for your single node job, or even for the multi-node job. So different knobs you can play with. The power will go down, of course. If you use less hardware, less power will be burned. Energy may also go down or up. I have an example later too. And typically the CPU and GPU time efficiencies, so what you get out, how much science you get out, will be better. Okay? You have better utilization of resources because the less parallelism you use, the better. Parallelism is good. It makes a program run faster, but it also means overhead. In summary, it's complicated. Okay? There's no single simple answer. I'm sorry. Sorry about that. Okay, so let's go through these things one by one. I'm trying to summarize a little bit to speed it up.
I have a doubt. In the last two slides, it said it's a trade-off between consumption and time and how much energy we are using. And what would be the ideal scenario? Basically, the thing is we want our work to be more faster, or basically to have more computations.
Yeah.
You want have less energy usage.
So the ideal scenario is you optimize your code to make it run faster. Because that usually means you use less energy. You could also reduce the clock speed. In some scenarios, reducing the clock speed does not do any harm to the performance. You will see an example later. You can reduce the clock speed without significant harm to the performance and still save significant energy. I'll show you later. That's the second ideal scenario. Okay, very quickly, optimizations of code. What could we do in terms of code optimization? We could use better algorithms. Okay, go from n squared to n log n. We have a very prominent example recently. We even did a video with an interview about it where people learned that choosing an algorithm with n log n is a huge game changer. Use optimized libraries instead of the standard open blast that you can download. Use MKL, so libraries that are optimized for the platform at hand. Use aggressive compiler optimizations. Don't be afraid of O-fast. Okay, so there's a lore that O-fast or O3 will break your code. Compilers make mistakes. Don't worry. Okay, just use high compiler optimization. Do less work. Okay, that's often overlooked. Can I do less work in my program? For example, I might be using dense linear algebra, dense matrices to do my stuff, but most of the entries in the matrix might be 0. So why not use sparse linear algebra? Does less work. Okay, doing less work means getting there faster. Also transferring less data, better. Balance the workload. Make sure that all your computing devices finish at the same time. It's called load balancing. If that's not the case, that is lock. Transfer less data from far away. And the further away the data is, the better. Okay, so that programming techniques, if you really have the source code in access, like cache blocking or register reuse, programming techniques that help you making better use of the data that's already loaded, loading less data multiple times, and avoid network communication. Make sure that the communication network is used as little as possible, not because transferring a byte costs so much energy, but because transferring a byte costs so much time. And hide the communication overhead. If two parts of your program on different devices have to communicate, try to hide that cost. For example, use bidirectional communication. Most of the communication paths on a computer are bidirectional. So use that feature. Or overlap data transfers with useful work. For example, on GPUs, you can overlap the data transfer from and to the GPU device with work on the device or on the host. Okay, so that's a very quick overview of optimizations, and a part of that is detailed on in our node-level performance engineering course, which is given for the next time in December in the RSNet. So if you're interested, you can learn more about that there. The second tuning knob is concurrency and how it influences resource efficiency. So the general rule is the less parallelism you use in your job, the better. That sounds weird from a computing center because we wanted to use our parallel systems. However, parallelism makes your program run faster usually, but also it has overhead. Okay. So here's a simple example. I have 4 processing elements, could be cores, could be GPUs or CPUs, doesn't matter. And they're doing parallel work, shown as P here and in green. But in doing so, they need to communicate. They need to talk to each other from time to time. For example, you might have some domain decomposition code that has to interchange halo cells for doing its work, the boundary conditions. These are the red arrows. And communication is overhead. It costs time. Time during which you cannot compute. Okay, if you cannot hide that time by some ingenious programming technique, it is exposed. And when communication is exposed, that's time you don't spend computing. There's time you don't spend computing, at least you burn the baseline power of the system. That's waste. Your code might be load imbalanced. Time to time, every code has to synchronize. All the processing elements have to synchronize to get to the same level. And if at that point, not everybody arrives at the same time, then others have to wait. Okay, there may be some waiting time if the load is not perfectly balanced. That does not mean that everybody has the same amount of work. It means that everybody takes the same amount of time to do the work. That's a difference. And then finally, this synchronization, like a barrier, for example, or some all reduction, some reduction that everybody needs some data from everybody else to do some computation, this also takes time. So load imbalance, communication, and synchronization. These are the 3 things that cost time, which is wasted, and also wastes energy, of course. So this means usually the less resources you use in your job, the less of that overhead you pay. If the green bars become bigger because you use less processing elements, then the red stuff becomes smaller in relation. Okay, so the less parallelism you use, the better. Of course, you want your job to finish in in 3 years, PhD time, whatever. Yeah, so there is some trade-off here. You don't want every job to run for 4 weeks. So usually that is true. Usually it's better to use less resources in parallel computing to have better utilization of the hardware. There's one exception. And the exception is if we have relevant shared resources. And that happens if you're on a single chip, on a single device, 1 GPU, 1 CPU, because there's lots of resources on those chips that are shared among all the computing elements that are on those chips. And to describe what the bottleneck is on the chip level, there's something very ingenious that people have thought of already in the 80s and that has been revived 20 years ago, which is called the roofline model. I will not go into details here. The roofline model shows you the expected performance of your code making 2 very simplistic assumptions. The first is there's a bottleneck of data transfer between the device and the memory, okay, because that costs a lot of time transferring data from memory and back. And there's a bottleneck in the computing units because there's some maximum performance at which you can crunch data. And we assume these are the only 2 bottlenecks in the hardware. Okay, how much time it takes to transfer the data and how much time it takes to do the actual work. Everything else is negligible. So that's our hardware model for this. And our software model is how many flops I do for every byte I transfer. Now let's say I'm doing a lot of flops in my code, a lot of computations for very little data that I transfer. That means I'll be running at peak performance because I'm getting a data byte from time to time, but then I'm doing a lot of floating point operations. So I'm running at basically peak performance. And this is in this diagram shown as this flat ceiling here. When the flop to byte ratio is very high, I'm running at peak performance. However, when the flop to byte ratio is very low, so I have to do 1 flop, but I need 16 bytes to do it. That's a lot of bytes per flop. That means mostly I'm waiting for the bytes to come in. The units which do the flops, they're bored, they're empty. Okay, and that means I'm memory bound. So I'm bound by the performance of the memory interface to get the data into the CPU. Now, if that happens, of course, the more flops I do per byte, the higher the performance. Okay? So the performance will be linear in this flop to byte ratio. And this is the left part of this diagram, which is limited by the memory bandwidth. So we have two situations now. I could be core bound by the computational performance of my cores. And that means I have a scalable code because it only addresses the computational units in my device. It doesn't address any data transfer bottlenecks at all. And then something interesting happens. What happens is that if you increase the number of cores that you use on the chip, increase the parallelism on the chip, you burn less and less energy because you get more performance from each core that you switch on. Okay. You also burn more power, but the performance is linear and the power is not linear in the number of cores. So what is shown here is the energy dissolution for some code, which is basically a code that does nothing but flops, versus the number of active cores. And you see it's a monotonically falling curve. So the more resources you use for this kind of code, kind of core-bound code, the less energy you burn. The power gets higher, of course, but the energy goes down. And this is a general rule. It's always true. We also have three curves here: scalar code, AVX code, AVX512 code. If you don't know what that means, don't worry. It's an in-core optimization using more effective instructions to do the work. And it shows here that the more effective instructions we use, the less energy we burn. All right, so that's core-bound behavior. Use as much parallelism as necessary or as possible on the chip to get the job done. This is most energy efficient. For a memory-bound code, this is not the case. For a memory-bound code, it means that if you increase the number of cores, the performance will go up, but at some point, the performance will saturate, will stop scaling. And from this point on, if you use more cores, you burn more power because you switch on all those cores, but you don't get more performance, which means the energy goes up. And this is the typical behavior of a memory-bound code shown here. Okay, energy goes down at the beginning, but at some point, the performance saturates, so the energy stays constant. And then if I still use more cores, energy goes up again. So this is significantly different from this picture. Now, showing it like that is really cumbersome, okay? Showing energy versus cores. And then there's also the topic of performance. Is it faster? Is it slower than before? Complicated stuff that can only be shown multiple graphs. For that, we have invented the Z-plot. It's called Z-plot because it was invented by our colleague Thomas Zeiser. And the Z-plot shows in an ingenious way how performance, energy, and the parameters that influence the two work together. The Z-plot shows energy on the y-axis and performance on the x-axis. Now, this is a Z-plot for a memory-bound code, a very strongly memory-bound code. There are three data sets here. Each data set is for one frequency. Black is for 2.2 gigahertz, green is for 1.8, and yellow is for 1.4 gigahertz. And along those data sets, this is the number of cores that we run. This is a memory-bound code. We know it will scale for some time, and then it will stop scaling as memory-bound codes go. And this is exactly what we see. Performance goes up, so we go to the right, but at some point it stops and it goes up. And this is the inset here. It stops scaling, so performance stays constant, even goes a little bit back, but the energy goes up. So this is a typical memory-bound behavior. Such code depend weakly on the clock frequency in terms of performance. So you can play with the clock frequency a lot without doing harm to the job's performance. That's a very interesting feature of those codes. The optimal operating point in terms of performance is where the performance just saturates. So you're at the maximum performance point, and then it stays flat. This is the point where you have least energy dissolution. So if you're aware of energy, then this may be the point to be at, using fewer cores than are actually available. The clock speed is something you can vary in a wide range. So here in this picture, we have three data sets, 2.2 down to 1.4 gigahertz. If we do that span, if you go down from 2.2 to 1.4 gigahertz, we lose about 3% of performance, very little performance loss. But we gain 36% in energy, gain in terms of we lose 36% of energy. So that's a huge win, okay, just for 3% of performance loss. So if your code is strongly memory bound, if you're dealing with large sparse matrices, linear solvers, for example, they're often memory bound, then this is a good scenario to play with clock frequency, to save a third of the energy for just a tiny sacrifice performance. You can use the set the concurrency with the typical means, setting the number of OpenMP threads, setting the number of MPI processes per domain, and so on. Whatever you use pinning, okay? You need to pin those threads and processes to these NUMA domains, because otherwise the OS will just do what it wants. The clock speed setting is also very simple. With Slurm, you can use the CPU frac argument, and you have to give a range of frequencies in kilohertz, ironically, so don't mix that up. If you do that, for example, to set it to 2 gigahertz, you say 2 million - 2 million performance for the governor, and that's it. It's very simple to use clock frequency fixing with Slurm. If your code is not memory bound, if it's core bound, scalable, so it scales well with the resources on the chip, then that's kind of a bad situation. It's good because it scales, of course, in terms of performance. It looks good also in graphs, But if there's no on-chip scaling bottleneck, you always have to use the full chip. Okay? That's also something you can show mathematically. You have to use the full chip to burn least energy. That's one thing. The second thing is the code is very sensitive to clock frequency. If the computational units are what bottlenecks your code, if you reduce the clock speed, you reduce the performance, proportionally usually. If you reduce it by 10%, you run 10% slower. And here's an example, again, with a peak flops code running with 2.2 and 1.8 gigahertz. So 10% clock speed reduction gives us exactly 10% performance reduction. And in this case, the power saving is negligible. For the modern CPUs we have today, clock speed reduction for scalable code, for core-bound code, does not pay off energy-wise, or just a little.
This is also true for turbo mode. So I assume that for turbo mode, at some point, the relation between frequency and power is not linear.
The question was, is it also true for turbo mode? Yeah, in general, for scalable code, there's an energy minimum versus frequency, and turbo mode is typically very inefficient. Of course, it makes your code run fast, but in terms of energy solution, it's the wrong part of the parameter space. Okay, so if that is your problem, if your problem is really core bound, then you're so sensitive to clock frequency, it doesn't really make sense to play around with it. Unless you're prepared to endure a lot of performance loss, less science per CPU hour. And usually you don't want that. So these are things that you can do as a user. I'll summarize them later. Now, what can the computing center do? This is just one slide, okay? What can we do to make all the operations more energy efficient, to burn less power, spend less money? There are two things, basically. We can fix the frequency or disable turbo mode, basically the same thing. So we set the frequency on Fritz to 2.4, 2.2 gigahertz and let you use it like that. Because turbo mode is typically very inefficient. If your code is memory bound, it doesn't give you any benefit. And if it's core bound, it runs faster, but uses overproportionally more energy. So let's fix the clock speed. That's what they do at Supermux, for example, at LRZ. The good thing is you have reliable performance behavior. There's no variation in clock speed anymore. Now, in turbo mode, the CPU can decide whether to run at 3.2, 3.3, 3.4 gigahertz, depending on many factors. For example, the ambient temperature. If you fix the clock speed, this is gone. So reliable performance behavior. There are still significant variations in power because what you run influences how much energy you burn, data transfer, computation, and so on. But these variations are damped a little bit because you cut off these big variations in clock speed. We have a pessimistic power limit. So it means that the power that each node burns at this constant frequency could still be different. If you do a statistic, you fix the frequency of all your nodes in the cluster, you run the same code on all of them, and you look at how much energy, how much power is dissipated on each socket, you see huge variations, plus minus 20, 30%. It's really huge. That means you have to design the power supply of the system to have like a pessimistic upper limit still, because these variations persist. So the infrastructure must provide some power headroom. You cannot build an infrastructure for a system that burns 1 megawatt on average with 1.1 megawatt. You have to be built for 2 megawatts. But that's an easy way to go. The other way is power capping. Power capping means you limit the wattage of each device. And it's very simple to do with GPUs or with the CPUs. For example, I could say each Fritz CPU cannot burn more than 180 watts. That will hard limit power dissipation of each device. But that means that the power variations across your devices translate into performance variations. Because one CPU may run at 180 watts with 1.8 gigahertz. The next one might do the same with 2 gigahertz. So you're translating the power variations across your devices into performance variations across your devices. You may not want that because it means that a job running on those CPUs will have different runtimes for all its CPUs. So you're introducing load imbalance artificially. So power variations turn into performance variations. The good thing is, from a computing center point of view, the infrastructure can be tightly power limited. So if I limit the power of my cluster to 1 megawatt, I can design my power supply to 1.05 megawatts and be fine because the power capping just works. That is good. I don't have to provide extra headroom for the power supply. So here's a picture from an older paper where they studied NVIDIA Volta GPUs and what happens if you power cap those GPUs. And it turns out as long as you stay above 180 watts-ish, the clock frequency stays the same, but then it goes down if you really turn the knob. But there's a considerable variation in clock frequency across devices because one device runs a little hotter, the other runs a little less hot. And if you clamp the power to a certain limit, then this variation turns into clock frequency variations, and you may not want that.
So as you said, you could set up a reliable power limit and power variations. So when it approaches, there can be two scenarios in which I think that first it lets the power usage go up till to the level and then it shuts down the CPU. or it optimizes it that it never reaches this level. So how does it allows it to reach one, like you said, 1 gigahertz watt, 1.8 gigahertz, and after that it shuts down, or like it never.
No, it doesn't shut down. There's a feedback loop that makes sure that if you run hot code that would otherwise be close to the thermal design limit, would run at a lower frequency. And cold code, which makes less use of the hot stuff of the CPU, will run at higher clock speeds. So that's a dynamic thing that happens within the CPU, and it's very reliable. So the CPU does everything in its power to keep within this limit. It doesn't shut off anything. It doesn't stop your job. It just adjusts its clock frequency so that the power dissipation is never beyond the limit that you set.
Okay, so when we have a system like that, we usually have these systems, and when the CPU shuts down or these kind of things overheating, then as per your idea, that's a different problem altogether. That's not.
Yeah, that's a different problem. If something shuts down, typically it means that it's misconfigured. Okay, so wrapping it up, what should you do? Because I've taken points of view of different people here, users of computers and computing center people. So what should you do as a user? To zeroth order, even if you don't care about energy and cost, what you should do is make your code run faster, because that is good for your CPU time allotment. You do more work per CPU hour, and it may also be good for power consumption, may or may not, depending on how the optimizations go. So how do you do that? You use the latest code versions, use the latest GROMACS. There was a blog post recently by Anna Kahler, which showed that it's really good to use the latest GROMACS versions. Use the best and latest compilers with high optimizations, best libraries optimized for the underlying architecture, and employ code optimizations. If you don't know how to do that, visit one of our courses. We teach you that. And second advice in zeroth order is avoid waste. Avoid times where nothing useful is done. So waiting for data, reasonable concurrency. If you have too much concurrency in your code, chances are you spend too much time doing nothing, waiting for data to be communicated, waiting for synchronization, or waiting for load balancing. Control the overhead. Use as little parallelism as possible. If it finishes in a tolerable time, don't scale further. You may run your code with a runtime of 24 hours, and you may see, okay, if I double the resources, I may run it in 13 hours. Go for the 24, because it's a better use of resources than running it in 13 hours for twice the resources, obviously. Unless it scales perfectly, which most codes don't. For memory-bound code, there may be some headroom to play with. You can have significant energy saving by reducing the clock speed for memory-bound code. Of course, you have to know whether or not your code is memory-bound, look into cluster cockpit, do some performance analysis. We can help you with that too. Run benchmarks, talk to us. And if all this is interesting to you, but you don't know when to do it, or your professor doesn't want you to do it during your time, consider applying for a Conveyor project. You know that Conveyor stands for Competence Network for Scientific High-Performance Computing in Bavaria. You can apply for short and long-term projects, which are specifically for sitting down with the computing center, optimizing your code, be it for energy or performance or whatever. So consider to do that. Thank you. Any questions?
And maybe I can ask that, for example, you mentioned that in the memory-bounded code, it is recommended to reduce the clock frequency, right?
Yeah.
For the energy saving. But in the previous slide, you also mentioned that if we reduce the clock frequency a lot, we can use the system for the longer time, which is also very not useful. So is there any kind of method that we can choose the optimal clock frequency, or how we can do that?
You have to know how your code behaves. Okay, so in this case, for the strong memory-bound code, the optimization area, the region in which you wiggle around, is this rectangle. Okay, so region where the code starts to saturate and separates and becomes insensitive to clock speed. So it doesn't make sense to just blindly reduce the clock speed to 1.4 gigahertz. You have to do some benchmarking and see when it becomes sensitive to clock speed and then stop there. There's a question in the chat, slide 16. Is energy use only the energy consumed by the CPU, or is it the total energy of the node? Yeah, that's a good question. It's always a very good question. So in these graphs, these were done by Stefan de Souza, one master student recently. This is only the CPU energy. Okay, it does not contain any contribution from the node in the rest, so fans or cooling or whatever, only the node. If you include that, you're giving more weight to the baseline power. Okay? You're giving more weight to the constant power contribution that you have no influence on, which means the power saving becomes less. If you include a constant baseline power of, I don't know, 50 watts, then all the differences in power consumption get smaller, and also in cost, of course, in terms of energy consumption. But as I said, 3/4 of the node are CPUs, so you're still good.